Alright, so we're in section 3.8. This is actually exercise 7. The book's example is really long, so I didn't want to put you through that one. But the idea is good. This is the blending problem, or blending section. And so this is our example. We have Eli Daisy is a made-up company name. They use two chemicals, 1 and 2, to produce two kinds of drugs, 1 and 2. So drug 1 must be at least 70% chemical 1. Drug 2 must be at least 60% chemical 2. And by the way, we're assuming that only the drugs are only made up of chemical 1 and chemical 2. Okay. Up to 40 ounces of drug 1 can be sold at $6 an ounce. Up to 30 ounces of drug 2 can be sold at $5 an ounce. Up to 45 ounces of chemical 1 can be purchased at $6 an ounce. Up to 40 ounces of chemical 2 can be purchased at $4 an ounce. We want to formulate a LP that will maximize our profit. Good. So in this case, probably the hardest thing is to come up with the decision variables. Of course, that's true in all of these problems. The decision variables here, so we're going to need to have some chemical 1 is going to be used in drug 1, and some chemical 1 is going to be used in drug 2, and similarly for drug chemical 2 and drug 2. So let's go ahead and say let Xij be the ounces of chemical I in drug J. Okay, so before we get into any of the constraints, let's think about how much chemical 1 do I have. So chemical 1 is going to be the first subscript, so that means X11 will have chemical 1, and the other variable for chemical 1 would be X12. And so similarly, right, chemical 2 would be X21 plus X22. And then how much drug 1 do we have? Well, drug 1 would be the second coordinate, or second subscript there, right? So drug J. So that would be X11, right, plus X21, right? And then drug 2 would be we want to fix the second coordinate to be 2 in this case. So that's 1, 2 plus X22. Good. All right. So keeping these amounts in mind, let's see if we can use our constraints. So let's see, the first constraint is drug 1 must be at least 70% chemical 1. So how would we do that? So drug 1, 70%, just to kind of keep things organized there. Good. Let's see. Well, that would mean the drug 1 in chemical 1, which is X11, divided by everything in drug 1. Drug 1 was what? X11 plus X21. And we would want that to be greater than or equal to 70%. Good. And so similarly for drug 2, chemical 2 in drug 2, which is X22, we would divide that by the total amount of drug 2 that we have. And we want that to be greater than or equal to 60%. Good. Now, of course, notice that these are not of the usual constraint form, right? So we would have to rewrite this as X11 is greater than or equal to 0.7 times X11 plus X21. And so to get this in our standard form then, let's see, that would be 1 minus 0.7 would be 0.3 X11, and then 0.7 times x21 just goes over as a negative, and so that would be greater than or equal to 0. And similarly, for drug 2, we would just multiply this over, right? And then bring things over. So the x12 now is going to have minus 0.6, and then we'll have 0.4 left over for x22 greater than or equal to 0. Good. All right. Now, these other constraints are pretty straightforward, right? So for example, up to 40 ounces of drug 1 can be sold at $6 an ounce. So therefore, you don't want to go over 40 ounces of drug 1. So we want 40 ounces of drug 1. So that means the amount of drug 1, which was x11 plus x21, should be less than or equal to 40, right? And similarly for drug 2, x12 plus x22 should be less than or equal to, what did we say, 30, right? Good. And similarly, I can't buy any more than 45 ounces of chemical 1 or 40 ounces of chemical 2. So those are also constraints in my problem. And so how much drug 1 do I have? That's x11 plus x21, right? Oop, that's drug 1. Chemical 1 is what I want. 1 plus 1, 2. x11 plus x12 should be less than or equal to 45. And last one, x21 plus x22 less than or equal to 40. Good. And now the last thing we have is our we haven't used the money yet, so incoming is going to be the $6 for each of the drugs, right? $6 for drug 1 plus $4 for drug 2. But then we have some costs. Oops, I'm sorry, I'm looking at the wrong thing. This is our incoming, right? These are our costs. And so yeah, so that'd be, let's see if we can write those down now. So the LP, the objective function is we want z equals $6 times drug 1, which is x11 plus x21, plus $5 for drug 2, which is x21, 1, 2. Let's see if I get it. 1, 2 plus 2, 2. Then our costs are minus $6 for chemical 1, which is x11 plus x12, minus $5 for chemical 2, x21 plus x22. And we really should simplify that a bit. If we do that, our z just turns out to be 2x21 minus x12 plus x22. It's interesting that x11 kind of fell right out of the problem. I guess that's because the incoming and outgoing balanced each other out. Good. So again, the main idea behind this problem was really in getting this decision variable set up. And again, we're using a subscript because we have different chemicals going for different drugs. Okay, very good. All right, there was another thing I wanted to talk about just briefly, and that was what we do if we have an unrestricted variable. So what to do with an unrestricted variable. Because notice in our LPs up to this point, our xi's have always been greater than or equal to 0. And we want to say, well, what happens if xi is just a real number? can I replace that, or can I substitute something so that the variable becomes all greater than or equal to 0 again. The reason we're doing this, by the way, is because for our theory, we're going to want to have all of our variables to be greater than or equal to 0. It makes the theory a little bit easier to work with. And so the idea is this. We're going to, if xi is unrestricted, introduce two new variables. We can call them xi plus and xi minus, although I don't usually use that notation. I'll show you what notation I use when we get there. It's kind of awkward in general. But then xi is going to be replaced by xi plus, the new variable, minus xi minus, where xi plus and xi minus are both greater than or equal to 0. Good. And so, yeah, that works really well for all of these. So let's do a specific example here. How about the following? How about if x2 is unrestricted? And I'm given an LP, let's see, how about I'm going to maximize 30x1 minus 4x2 such that 5x1 minus x2 is less than or equal to 30, and x1 is less than or equal to 5. x1 is greater than or equal to 0, but x2 is unrestricted in sign. URS, by the way, is the unrestricted thing. Then, to get around the unrestricted in sign problem, we will let x2 be equal to x3 minus x4, where x3 and x4 are greater than or equal to 0. Okay, and in doing that, we now have max 30x1 minus 4 times x3 minus x4, such that 5x1 minus x3 minus x4 is less than or equal to 30, and x1 is less than or equal to 5, and now x1, x3, and x4 are all greater than or equal to 0. Good. So in introducing these new variables, we were able to get rid of this unrestricted in sign variable and replace it by all variables that are greater than or equal to 0. Easy. So we're actually going to look at this again later, but I wanted to introduce it now because some of the problems that we're going to be working with in the examples ask us to do this. Okay, so this is a little bit of foreshadowing. All right, that's it. I will see you in the next video.